Hi, my name is Nishant, and I chose the topic dynamic modeling of a four-wheel vehicle. And I just used two subsections to describe my presentation: vehicle states and vehicle dynamic modeling. If you go further into it, you have to learn about vehicle dynamic simulation and map representations. Vehicle dynamic simulations just simulate the vehicle we model into the simulation environments, and map representations is like the map the vehicle follows. So yeah, if you want to go in deep after that, you have to learn about that also, like vehicle states, dynamic modeling, and simulations and representations. Let's start with system dynamic. So system dynamic is a mathematical description of the relationship between an input signal u and an output signal y. So for an example, if you want to turn a car, input would be the steering angle and output would be the turn. And it's usually described in the form of ODE. ODE is ordinary differential equation, which states the relation between multiple variables, and also in the form of states. Dynamics is like states, which changes when the vehicle changes its behavior in the environment. So, in short, states describe the behavior of a vehicle in the environment. Suppose a vehicle is at rest, so state would be zero. State would be at rest. So the acceleration is zero. Because the acceleration is zero, state would be at rest. It's described like a vehicle is staying at a normal, like a particular place, not even moving. So it describes the vehicle behavior in the environment. These variables, like it's an x variable. So if the x changes, behavior of vehicle also changes. So it helps us formulate a system behavior in the form of ODEs. So for the ODEs, I'll just turn to the next slide after describing the standard system description. So standard system description consists of a system dynamics and output equation. So system dynamics tells us the relation between initial states and the input signals. I'll repeat it again. So it tells us the relation between inputs and the initial state. Suppose initial state is acceleration is zero, and the state is at rest. So input is nothing, and this initial state is at rest. So describe like vehicle is not moving. Whereas output equation describes a relation between the state and the output. So after giving the inputs and after giving the initial state, what comes as output, and it describes the relation between that output and the if suppose output is like acceleration equal to 20 kilometers per hour. So it would describe the relation between that acceleration and at that vehicle state at that particular time. I'll turn to equation now. So equation is this: x differential. So what is differential is like x depends on multiple derivatives of variables. So it's called differential. X is the current state. So it could be zero, acceleration might be zero, acceleration might be 20 kilometer per hour. It's unknown. And yeah, we can know like in real life we know the state. And for the input matrix, like every environment like has a matrix like a coordinate system. So it's the input matrix. U is the output signal. It's the relation between initial state and the output signal. And so here comes the equation I was talking about, that, which name output equation. So it tells us the relation between the output as well as the this thing differential, right? So it was a state. So the equation which tells us the relation between the state and the output is termed as output equation. Next topic is vehicle states. So what is vehicle state? Vehicle state defines the vehicle behavior or position in the environment. So basically, the current state can be at rest or moving at an acceleration, moving at a velocity, or making a turn or making a steering turn. It could be anything. And it's basically like most of the time it's derived from sensors, rather it be GPS or odometers, camera, or LiDAR sensors. And I have learned all of these in class. GPS for mapping and things, odometer for speeds, gyrometer for speeds, camera for detecting anything if it's in front, and LiDAR for creating a map. And next thing is position. Position state. What is position state? So position is a coordinate vector. What does a vector mean? Vector means like it has a direction as well as some value. So it's a directional value is termed as a position. And this is respective to the center of gravity of the vehicle, and it's located in the coordinate system. So x coordinate, y coordinate, and it's normal in meters. And most important, the environment needs to be known, like what's in the environment, right? So that we can measure the coordinate system. So from the x-axis, like from the so it's the sorry, it's the x, it's the y, and it's the z. So it's x and y 2D plane. We can just locate the vehicle position, and it's called the position state. Next thing is steering hand angle and heading. Okay, so this is heading and this is steering angle. So steering angle describes an angle that displays the direction in which the front wheel currently looks at. So basically, when you drive a car, so what position or what direction our front wheels are looking at, it's called the steering angle. Suppose we say steer to the left. So if we turn steering to the left, our wheels look at a steering angle with respect to the center line. Center line is perpendicular to the lateral axis of the car. So it's basically z axis on the respect to the center line, like it's a tangential line to the center of gravity, to the ground, not like this but straight one. Yes, so if it's x, y, and it's the z thing. Yes, steering angle should be the same for both wheels, and it's represented in radians or in degrees. The second is heading. What is a heading? So heading defines an angle in the direction which currently looks at. Okay, it's respected to the x axis. It's the z axis. X and y represents the position, and z axis represent the heading angle. Heading angle is also in radian or degrees, and it can range from minus pi to plus pi. That is 0 to 360 degrees, and sorry, 180 minus 180 to 180 degrees, like anti-rotating and rotating. And for that, or it could be 0 to 2 pi. What is 2 pi? 2 pi is like 360 degrees, 0 to 360 degrees. And it's only applicable while rotating. Next one is acceleration and velocity. For acceleration, velocity, acceleration is like when you give your vehicle a direction, it's termed as acceleration, and when you don't give your vehicle an acceleration, is termed as velocity. So let's go with velocity first. So it shows vx, like velocity in x-axis, velocity in y-axis. So basically, it's the value, not the direction. Okay, if you give the direction, velocity becomes acceleration. If you say drive 10 kilometers per hour in left direction, it's an acceleration. Okay, if you say drive 10 kilometers, it could be in any direction, right? It's non-directional thing. You didn't give any direction, so it's called the velocity. And there is a formula to find absolute velocity. It's the absolute velocity is equal to, like, how do we find this one? It's the square of velocity on x-axis, square of velocity on y-axis, and its root. It's easy to find absolute velocity, and normally it's in meter per second. And if we go here, it's meter per second square. I'll explain that in a minute. And velocity is usually measured by IMUs or wheel sensors, and velocity can be accurately provided by only pivot sensors. What are pivot sensors in class? I do remember. So the Formula cars have something like pointing outwards like a pipe. That's called the velocity sensors or pivot sensors. Now coming on to acceleration. Acceleration is like when vehicle gets the direction or change its states in x-axis or y-axis. Okay, it can be longitudinal or lateral. Longitudinal is ax and lateral is ay with respect to the ground, right or left with respect to the ground. Okay, so there should be a respective environment so that we can observe the acceleration. It is also measured with IMU sensors, and it's usually in meter per second square. So I forgot the formula for acceleration. It should be acceleration equals to force into something. Oh, sorry, mass into acceleration is force, right? F equals to m into a. Yeah, F equals to ma. Yes, F is equals to ma. So basically, applying the force to the direction in acceleration results in moving of vehicle. That was it. So moving on, the next position is okay. So till now, before I go to question, so there are some more position states also, such as lateral angles, longitudinal angles, steering angles, slip angles, wheel slip, and more. So basically, when we turn a car at a higher speed, so it's called a steering angle or wheel slip angle. Wheel slip, sorry, it's called a steering angle. So again, wrong. It's called a slip angle. So when you turn at a car at higher speed, it's called a slip angle. Wheel slip is when we like when the car emits the smoke. So when we try to run the tires like so it's called the wheel slip. And there are many more angles like the Frenet frame 1, Frenet frame 2, but this thing was getting out of scope. So I thought I would stop here about the states and just move to the modeling. Before I move to modeling, I would like to ask a question: which trajectory is the car following in? So if we go to the steering angle, this should be B, right? Because our tires are looking at B. Like what do we get from the steering angle? Like which are currently tire looking at? It's looking at B, but it's not true because we don't have the acceleration. Like we don't know where the car is going, so we cannot predict the trajectory of the car by only these angles. So we need to understand Frenet frame 1 and Frenet frame 2. So Frenet frame 1 and Frenet frame 2 brings various parameters into consideration. Okay. So from position, from like starting from the first state to the end state, like Frenet frame 1, Frenet frame 2, the parameters do increase and accuracy also do increase. Okay. So while we reach to the Frenet frame 1 and Frenet frame 2, which I'm not discussing in this one, but yeah, that is important. So it basically focuses on turning the cars on a high speed angles. Okay. So when you are at high speed and it tells us like what should be the angles and things, and it brings into consideration that thing. So now the question arises, why modeling? So basically with modeling, we get a certain models to implement on real vehicles. So we did everything in labs, from positions, we need this angle, we need everything. We did everything in labs, calculated differential equations. We did every relations. We did analytics for the graphs, errors, and things. We did everything. But it's time to implement on real vehicles, right? So we do inputs, and it's implemented to real vehicle. And modeling helps us reach our outputs accurately, and it matches our goal. Okay, so that's the reason why I need modeling. So basically, model types, there are four categories of model types. It's called a single track model, double track model, multi-body simulation, and the finite element simulation. Okay, as we go from left to right, or from single track to finite element simulations, the number of parameters increase. What I mean by that is, suppose if you want to implement something in braking system in finite element simulation, or like if you want to implement anything, for example, brakes, okay, you need to know brake size, diameter, every possibility of every menu things you need to know. So basically, if you go from left to right, number of parameters increases, accuracy also increases, but the difficulty to implement them also increases. Various angles, things comes into consideration when you implement these types of models. To start with, there are 6 degrees of freedom in cars. So it's X, Y, and Z. Okay. So a car can like a roll motion, like along a x-axis, pitch. Yeah, we did this in class. It's easy. Next thing, single track model. For the single track model, it's basically called kinematic single track model. In this thing, the prerequisites are it's a slow driving vehicle, slow speeds, cornering is sorry. First thing first, we'll go to single track. It's a single track model. For single track model, we need like it's a basic one. It's like no roll, no pitch, no turns, no wheel load. It's small angles. Like it's kind of not possible. Okay, so it's like it's just for our reference. Like to start with, what do we need to start with? Then it comes the kinematic track model, which is little bit. There's a little bit of possibility to implement kinematic single track model. What does it do? Like, these are like small angles. Okay, for the front wheel. Now comes the single track model. Single track model is implemented. It can be only implemented while the vehicle is driving slow speeds. It's cornering very slowly. Like there is no lateral is this, longitudinal is this. There is no lateral acceleration. because it wouldn't be able to make a turn. Okay, there's no like the tire roll along the longitudinal axis, not like this, like not while turning. Tire will not rotate while turning; it will rotate while just moving forward. Okay, there are no little forces, no slip angles. It's also kind of hypothetic. Like it's it can be implemented, but it's not that possible. And there is a famous angle in this Ackermann angle, and it's a whole theory on Ackermann angle. So with this guy, that's like how to find how to find an Acker. Where's the mouse? Okay, how to find this angle, and it guides us like what all values should be there. Next comes the yeah linear single track model and non-linear single track model. Both are the same, but in non-linear, there come the tire forces, but in that there are no tire forces. Okay, so let's do linear single track model. Its velocity assumption is zero. Just the difference between this model and the single track model, like the previous models, is like the normal single track model is like vehicle forces, tire forces come into play, like frictions, coefficient of frictions, forces do come into play. And there's something called cornering stiffness in the tires. That's also like all the forces that act on tire come into this model. And for the non-linear and linear, these both are the same thing. These both are kind of same thing, but there's a difference between the angles, getting angles and things.
Evasive maneuvers.
Next one is non-linear single track model, and there are some equations which I don't think so. There's a need to go on because those are really getting out of scope. Yeah, and just yeah. So basic difference between linear and non-linear is in linear there like less tire forces, and in non-linear there come the more tire force in the side slip angle and like a little bit more, not much more, but a little bit more. And there was something called there were two models, Yala and Packager Magic Formula, which came into existence for this thing. I didn't went into that deep because that was getting hard and hard. So I just kept it till here. Like, what's the major difference between linear and single? A linear single track and non-linear single track is just the tire forces. Next comes a double track model. The most efficient is double track model. It's the main one. It considers everything. It considers center of gravity. It considers every forces. It also considers the rolling, pitching, vehicle load, axle load. It covers everything you can imagine in a vehicle. And this is mostly implemented in like vehicles. And there's a project in University of Waterloo. It's going on an autonomous Lincoln. It's Lincoln vehicle, and the vehicle name is Moose. And they do implement these type of modeling on that vehicle. And that was it. And to just like when we go in labs, we implement these in a simulation environment using various models and things so that we can achieve our purpose of modeling, dynamic modeling of four-wheel vehicle in a good manner.